The last topic we're going to discuss in this chapter is solving quadratic inequalities. Let's look at our first example. So we want to solve x squared minus 6x minus 27 is less than or equal to 0. So again, when you need to remember, anytime the directions say solve, our goal is to find any numbers, any values of x, that if we substitute into this statement, into this inequality, then we'll get a true statement, or basically any value that makes that number squared minus 6 times that minus 27 a value that's less than or equal to 0. So in order to find the solutions when we're working with solving quadratic inequalities, so inequalities would have the less than, the greater than, rather than just the equal. That's how you would differentiate between just solving a quadratic equation versus a quadratic inequality. And so when we are solving quadratic inequalities, we're going to first find the values of x that make the left-hand side equal 0. Okay, so basically we're just going to take our x squared minus 6x minus 27, set it equal to 0, and solve that equation. So x squared minus 6x minus 27 equals 0. This is factorable, so I can factor x minus 9 times x plus 3 is the factorization. So our solutions are 9 and negative 3. So once we find the values that make this equal 0, then we can take those values and place them on the number line. Okay, so we'll take the 9 and the negative 3, and negative 3 is to the left. Make sure you are placing them at least with respect to each other in an appropriate location. So we'll put the numbers that we find, the real numbers that we find, on the real number line. And then, so these are the values of x that make this equal 0. So we're looking for any number that makes x squared minus 6x minus 27 less than 0 or equal to 0. Since these are the values that make it equal to 0, they are going to be part of the solution set, so we will shade them in. Okay? So now we're looking for the numbers that make this less than 0. And it's always going to be that once you determine what numbers make it equal to 0, then you can test the regions that are created. So these two numbers basically took our number line and split it into 1, 2, 3 separate regions. And it's going to be either that every number in a region is a solution, or that no number in that region is a solution. So if we want to find the other solutions to this inequality, all we need to do then is use a test point in each region to find the regions of solutions. So use any number that you want to the left of negative 3. I'll try negative 5. We can test any number in between negative 3 and 9. You could use 1. And any number from 9 to infinity. So let's say 10. So we're going to substitute these in to see if they are solutions. So if we substitute negative 5 into our inequality, we'll have negative 5 quantity squared minus 6 times negative 5 minus 27. So doing that on the calculator, we get 25. That's 25. 6 times negative 5 is negative 30. So minus the negative, we'll have 25 plus 30 minus 27. So the 25 plus 30 is 55. And 55 minus 27, we end up with 28. So is it true that 28 is less than or equal to 0? And that would be no. The numbers that are less than 0 are negative numbers. So it would have to be that when we substitute negative 5 in on the left-hand side, we'd have to get a negative number for it to be a value that's less than 0. So negative 5 is not a solution. And since negative 5 is a solution, it's always going to be the case then that neither is any other number in that region. So I only shade, when we're working with number lines, we shade solutions. Negative 5 is not, therefore nothing is, so this region should not be shaded. Okay, so that means we don't shade. Okay, so let's try 1. So now if we're checking to see if this is a region of solutions, we're going to substitute 1 into our inequality. So we have 1 squared minus 6 times 1 minus 27 is less than or equal to 0. So that's 1 minus 6 minus 27. So you can do that on your calculator, but I can already tell if I do 1 minus 6 minus 27, then I'm going to end up with some negative number, and every negative number is less than 0. So that tells me that 1 is a solution and that I should shade in between negative 3 and 9, because remember, if any number in this region is a solution, that means every number in that region is a solution. And finally, we're going to test the region to the right of the 9. So substituting 10, we have 10 squared minus 6 times 10 minus 27. So that's 100 minus 60, that would be 40. And 40 minus 27, that's 13. That's a positive number. So that's less than 0. That is not true. So 10 is not a solution. So the solutions to this inequality are all the numbers from negative 3 to positive 9, including both the negative 3 and the 9. So if I were to write my solutions using interval notation, I would say that every number from negative 3 to positive 9 inclusive are solutions to this this quadratic inequality. Okay? Same thing. So it's solving a quadratic because we have the x squared, inequality because we have the inequality symbol. So anytime, and regardless of whether it has the or equal to bar or not, if you're trying to solve I'm having a hard time today. If you're trying to solve quadratic inequalities, then you always want to first find the numbers that make this equal to 0. So you take your left-hand side here, your x squared, LHS stands for left-hand side. So your x squared minus 4x plus 1, you set it equal to 0, and then you solve this equation. So, this whole chapter has been about solving quadratic equations. Looking at this, it's not factorable, so I could either solve by completing the square or using the quadratic formula. Because this number is even, I think it's easy to complete the square. So I'm going to do it that way. So I've got x squared minus 4x plus something equals my negative 1 plus something. So I know that I want this to be a perfect square, or to factor into two binomials that are the same. Based on just the first two terms, those binomials both have to be x minus 2 for inner and outer to add to negative 4x. Therefore, the number that would make this a perfect square is the product of negative 2 times negative 2, or positive 4. So negative 1 plus 4, I get 3 on the right-hand side. So now I have x minus 2, quantity squared, is equal to 3. So now that I've got something squared equals a number, I can take the square root of both sides to solve. So we have x minus 2 equals plus or minus the square root of 3. Adding the 2 to both sides, we get 2 plus or minus the square root of 3. So once I find these solutions, then I can take those numbers, and those are real numbers, right? There's no i's, so they are real numbers. I can take these numbers and I can place them on the number line. So I take those. So one number is 2 plus root 3, the other is 2 minus. So the 2 minus root 3 is obviously the smaller, and the 2 plus would be the larger. Okay? And so once we have partitioned our number line, then we can go ahead and test our regions. But in order for you to be able to test your regions, you're going to have to know approximately what the value of these numbers are. So just in your calculator, type in, can you see here, the 2 minus, here I'll type it and then show you, 2 minus the square root of 3. And so I get that that's approximately 0.3. Similarly, I can look at the value of 2 plus the approximate value of 2 plus root 3, and that is 3.7. So this guy here, it's approximately 0.3, and this is approximately 3.7. And so that's necessary for me to know a number to the left, a number in between, and a number to the right. So I can use any number that's to the left of 0.3. I'm going to use 0 just because I can. So 0. Any number you want between 0.3 and 3.7, so let's say 2. And any number you want to the right of 3.7, let's say maybe 4. So just decide if the region is a region of solutions. We have to substitute these values in. So when we put 0 in for x, that's 0. 4 times 0 is 0. So 0 minus 0 plus 1, we get 1. And 1 is greater than 0. So when we substitute 0 in, we get a true statement, which means that 0 is a solution, and that every number to the left of 2 minus root 3 is. Now, 2 minus root 3, remember, is a value that of x that makes this equal 0. And since there's no bar underneath, we're not looking for numbers that would make it equal to 0, or the numbers that make it equal to 0 are actually not part of the solution set. So we should have open circles instead of closed circles at those boundary points. Okay, when I put 2 in for x, I have 2 squared, so that would be 4 minus 4 times 2 plus 1. So 4 minus 8 is negative 4. Negative 4 plus 1, we get negative 3. Negative 3 is greater than 0. That is not true. Therefore, 2 is not a solution. Therefore, this region is not a region of solutions. Okay? Last, substitute the 4. So if we do 4 squared, we have 16 minus 4 times 4 plus 1 is greater than 0. So 16 minus 16 is 0. Plus 1 is 1. 1 is greater than 0. That's true. So when we substitute 4, we do get a true statement, which means 4 is a solution, and therefore every number in that region is also a solution. So the solutions, or the numbers that satisfy this inequality, are all of the numbers from negative infinity to 2 minus root 3. And then every number from 2 plus root 3 to positive infinity. Again, solving this quadratic inequality. So we want to start by setting it equal to 0 and solving. So we have our equation x squared minus 8x plus 20 equals 0. If this were a minus, it would factor, but because it's not, this isn't factorable, so again we'll have to either solve using the quadratic formula or by completing the square. Again, I'm going to complete the square just because it's easy when the coefficient of the x is even and the lead coefficient is 1. So we have x squared minus 8x plus something equals our negative 20. I'm subtracting the 20 from both sides, plus whatever we add to the left. So for this to be a perfect square, it has to factor into two binomials that are the same, and those two binomials are going to have to be x minus 4 in order for us to get our negative 8x in the middle. Therefore, the number that completes the square is the product of these two. So this number is 16, as is this. So we have x minus 4 quantity squared equals negative 4. We take the square root of both sides, and we have x minus 4 equals plus or minus 2i, or getting x by itself from that point, adding 4 gives us x equals 4 plus or minus 2i. Okay, after we find those solutions, then we place them on the number line. But remember, this is the real number line. Okay, and it's only real solutions that we're looking for here. Okay, or if you get complex numbers, can't really see that now, but you can't place complex numbers on the real number line. So in the last example, when we found these values of x that made our quadratic inequality equal to 0, or quadratic x squared minus 8x plus 20 equal to 0, then we would take those and place them onto the number line. And what it would do is basically partition our number line into regions and non-regions of solutions. Well, here I wasn't able to partition my number line at all. Okay, so what that's going to mean when you come to situations like this, it's either then going to be that every number on the number line is going to be a solution, or that none of the numbers on the number line are solutions. So what we need to do at this point is basically just test any real number. Okay? If that number makes that statement true, that means that every number on the number line is a solution. If it doesn't, then that means there are no solutions. So it's either going to be all real numbers, or it's going to be no solutions. Okay, so in this case, you can test any real number you want. So let's say you want to test the number 1. If you substitute 1 in, you have 1 squared minus 8 times 1 plus 20. It's greater than or equal to 0. 1 minus 8 is negative 7. Negative 7 plus 20 is 13. And 13 is a number that's greater than or equal to 0. It's greater than 0. So 1 is a solution. So if one of the numbers is a solution, that means every number is a solution. So we should shade the entire number line. If I had substituted 1 into the equation and it was a false statement, then I would say that this quadratic inequality has no solution. So in this case, every number, all real numbers from negative infinity to positive infinity, will satisfy this quadratic inequality. They are solutions to this quadratic inequality. Okay? So that is how you can find solutions to quadratic inequalities using this method. There's also an optional method, or an additional method that kind of you're using what you've known, what you've learned about graphing quadratic equations in two variables and kind of connecting to what we're doing here. So if we're considering the graph of this parabola, y equals x squared minus 6x minus 27, okay? What we know, because we have the x squared, we know it's going to be a parabola. And we know that because the value of a is positive, that it's going to be a parabola that opens up. Okay? And so it's going to end up looking something like this. Okay? If I was wanting you to take this and find the x-intercepts, you would let y equal 0 and solve for x. Okay? So if I was asking you, this is what you would do, or what you would solve to find x-intercepts. Right? So if we solve this equation here, that equals 0. We've done this, this was the very first problem that we did. X equals 9 and negative 3. That's actually our x-intercepts. Okay? So that's our x-axis, and this is our y-axis. Then we found that negative 3, 0 is an x-intercept and positive 9, 0 is a y-intercept. So going through this, I can see for any x values that are to the, looking at my picture, if I input any value of x that's to the left of negative 3, the corresponding output, the corresponding y value, is going to be some positive number because my parabola is above the x-axis. Okay? Also, if I substitute any number between negative 3 and positive 9, since my parabola is below, I know that for x values between negative 3 and positive 9, the corresponding output is always going to be a negative y value. So, where does x squared minus 6x minus 27 equal 0? That's at the intercepts. Where does x squared minus 6x minus 20, or where is it greater than 0? So that means if I substitute a number for x, the output, the y, is greater than 0 if I'm to the left of negative 3 or to the right of positive 9. So that's from negative infinity to negative 3, and then from positive 9 to infinity. And where is this less than 0? So for what values of x is the output negative? That's numbers between negative 3 and positive 9. Okay? So if we go back to, let's go back to these. So that one we just did. So if we wanted to solve this, when we solve x squared minus 4x plus 1 equals 0, that would correspond to x-intercepts on that corresponding parabola. Okay? And because a is positive, we would know if we were putting something like this in the two-dimensional world, that we would end up with a parabola opening up with these being the x-intercepts. So we can see that to the left of 2 minus root 3, the corresponding output, or the corresponding values, are going to be greater than 0. They're positive. Right? And if the parabola is below, that's when it's going to be less than 0 for those values there. Okay? So you can use whatever. If you didn't understand the connection between the parabola, that's fine. You can always just continue on with the test points. So here, it works for, other polynomial inequalities, not specifically just quadratic inequalities. Here, this would be, if we multiplied it out, the highest degree would be 3, so we wouldn't call it a quadratic inequality anymore. But the same process applies. The first thing you would want to do is solve the equation where you have this x minus 1 times the quantity x plus 2 times the quantity x minus 4 equal to 0. So this times this times this equals 0. We've dealt with this a lot. The only way you can get a product of 0 is if you use numbers that make the factors equal to 0. So this product would equal 0 if x is 1, negative 2, or positive 4. So once you get those numbers, then you take those numbers and you place them on the number line. Again, make sure you put the smallest number to the furthest left and work your way up. So we've got negative 2, then 1, then 4. So here we've actually split our number line into 4 regions. 1, 2, 3, 4. So we'll have to test, if we're using the testing, we're going to have to test all 4 regions. So we can substitute, let's try negative 3. Any number you want between negative 2 and 1, let's do 0. Any number you want between 1 and 4, I'm going to do 2. And any number to the right of 4, I'm going to do 5. Okay? And so we're going to take those numbers and substitute them in and see if we get a true statement or a false statement. If it's true, it means that negative 3 is a solution and that every number in that region is also a solution. If it's false, it is not, and I should not shade that region. Okay, so if I put negative 3 in, I have negative 3 minus 1 times negative 3 plus 2 times negative 3 minus 4. And I'm not even going to bother with finding out exactly what this product is, because I know that I just want it to end up being something that's greater than 0. And for it to be greater than 0, it's going to have to be a positive number. So negative 3 minus 1, that's negative 4. Negative 3 plus 2, that's negative 1. Negative 3 minus 7, that's negative 7. And if I multiply a negative by a negative by a negative, that's going to end up being a negative number. Negative 28 specifically. So negative greater than 0, it is not. So negative 3 is not a solution, and I should not shade that region. Okay, if I substitute the 0 in, then I'm going to have 0 minus 1, so that's going to be a negative number. If I put 0 in here, 0 plus 2, I'm just going to write this down here actually, so negative. 0 plus 2, that's a positive. And 0 minus 4, that's a negative. And like I said, I really only have to pay attention to the signs. If I multiply these two negatives, it's going to be a positive times a positive. That will be a positive number. So if I substitute 0 in, the left-hand side will be positive or greater than 0. So I should shade in between. And also, my solutions are numbers that make this greater than or equal to 0. These were the values of x that make it equal to 0. So with the bar here, these numbers need to be shaded. So negative 2, positive 1, and positive 4 are all solutions, as are, so far, we found every number between negative 2 and 1. So if we substitute 2 into our inequality, so 2 minus 1, that would be a positive number. 2 plus 2, that's a positive number. And 2 minus 4, that's a negative number. So if you multiply two positives, you'll get a positive. Then times the negative would be a negative. And so a negative greater than 0, it is not. And then finally substituting the 5. So 5 minus 1, that's a positive value. 5 plus 2, 7, that's a positive number. 5 minus 4, that's a positive. And so if we multiply three positives, we will get a positive, and every positive is greater than 0. So we also need to shade every number to the right of 4. So from my graph, I can see that every number from -2 to +1, or every number from 4 to infinity, will satisfy this polynomial inequality. Okay, last one. Solving this polynomial inequality. So again, first things first, you want to find the numbers that make it equal to 0. So x minus 10 to the third times x plus 4 squared times x minus 4 equals 0. That's what we want to find. So still, the only way this product will be 0 is if I multiply, if at least one of those factors is 0. So if x is 10, that factor would be 0. If x is -4, that factor would be 0. And if x is +4, that factor would equal 0. So 10, -4, and +4 are the values of x that will make this product equal 0. And so now, once I find those values, then I go ahead and place them on the number line. So the -4 is furthest to the left, then the +4, then the 10. Okay, so now I need to, again, I have 4 regions to check. So any number to the left of -4, I'm going to go -5. Any number between -4 and 4, I'm going to go 0. Any number between 4 and 10, I'll say +5. Any number to the right of 10, I'll check 11. So if I put -5 in here, -5 minus 10, that would be some negative number that we're going to raise to the third power. If I put -5 in here, -5 plus 4, that's -1, but it doesn't matter. Negative number that we're going to multiply twice. And then I'm going to have a -5 minus 4. That's going to be a negative number that we just multiply once. So what we have, a negative times a negative times a negative, that would be negative. A negative times a negative, that will be positive. And then times that remaining negative, this will end up being a positive product, because these two negatives, when we multiply, will give us positive. So if I substitute -5 in, I'll get a positive number, and every positive number is greater than 0. So -5 is the solution, as is this entire region. Also, since I have the or equal to, I should go ahead and shade, because the numbers that make the left-hand side equal 0 are also solutions. If I substitute 0 in, 0 minus 10, I'm going to have a negative number to the third power. 0 plus 4, that's going to be a positive number squared. And 0 minus 4, that's going to be a negative number. So if I multiply this negative 3 times, I'll get a negative. A positive twice, I'll get a positive. And so again, if I multiply these two negatives, this will be a positive, so 0 should satisfy. So I want to go ahead and shade this region as well as the 4. Okay, and I already know the 10 will be shaded too. If I substitute 5 in, 5 minus 10, we get a negative number to the third power. 5 plus 4, we get a positive number that we will square. And 5 minus 4, we get a positive number. So this is a negative times a positive times a positive, and that would give us a negative product. So 5 is not a solution, and neither is any number in that region. And last but not least, we have to check this region, substitute the 11. 11 minus 10 is a 1, or positive number. 11, so and we'll have a positive to the third. 11 plus 4 is a positive number that we will square. And 11 minus 4 is a positive, and if we multiply all positives together, that product will be positive as well. So we need to go ahead then and shade this entire region. So based on my shading, I see that I have every number from negative infinity to positive 4 shaded, and every number from 10 to infinity. So my solutions are every number from negative infinity to 4, and then from 10 to infinity. It's not necessary to break this up because there is no break in the interval. It is every number from negative infinity to positive 4 that is shaded. So if you need any extra help, or if you want more work on that connection between the graphing and finding the regions to shade, let me know and I'll be glad to help. Good luck!